In 1898, a man named Veblen published an article in the Quarterly Journal of Economics called "Why is Economics Not an Evolutionary Science?" Okay, this is the statement summary for last week. We're up a little bit. Now I'm going to show you a chart for the lifetime of the trader because it's much easier to understand and read. Now the y-axis is the actual number of pounds we're up over the opening of the account. So right now we're about 700, we're a little over 700 pounds up. A man named Veblen published an article called "Why is Economics Not an Evolutionary Science?" Now, economists as a whole, eager to grab hold of the latest scientific developments, went, nah, it'll be fine. This group of brilliant economists then went on to discover such amazing things such as unemployment is necessary and desirable and policy should be written accordingly. They also discovered that you only need a single consumer to understand all things in the economy. And they discovered, most importantly perhaps, that rich people were good and wholesome for society. The richer the better, because the richer they were, the more they could innovate, the better all our lives would be. Now the banks were so impressed by this deductive magnificence that they created a memorial prize. Now they needed their memorial prize to have a bit of gravitas, so they named it the Memorial Prize in honor of Alfred Nobel. And then, in a cunning move, they shortened it to the Nobel Prize of Economics. The key takeaway here is, if you're modeling the economy with a single representative agent, there is no possible way you are going to see emergent behavior, evolution, or any of the key systemic forces that arise in any natural system that is populated by multiple agents. So what do you need for evolution? Well, okay, instead of a single identical consumer, imagine that people were different desires and different capabilities. That's condition number one necessary for evolution. Condition number two, imagine that people who were more successful were looked to and imitated. So in other words, successful people would write books and go, this is how to make money in trading, or this is how to be successful in economics, or whatever. That would be called imitation. So the poorer agents would be imitating the more successful agents. That's the second condition, and if you have that working over time, you will have evolution. Of course, the most interesting thing is, what are those evolutionary forces doing? So today, we're going to go back to 1898, and we're going to pretend that science was taken seriously in economics, and I'm going to show you exactly what evolution is and how it applies to economics, even to such elementary things as price. The first evolutionary model I'm going to show you was published in a scientific paper and also adopted by the Santa Fe Institute as a teaching tool. Now, it's, in my opinion, much more complicated than it needs to be, which I'm going to show you. But I wanted to start with something that was acknowledged as true evolution before I move it to, shall we say, Tim-style evolution. Okay. This is Netlogo, and this is an academic program that is typically used to help students to learn about multi-agent programming, multi-agent models, and multi-agent models are typically used to understand emergent behavior and evolution. In fact, it's the only modeling technique I'm aware of that can do evolution. It's an academic program, so quite safe, and it runs on Windows, Macintosh, and Linux, and it's free to download. Now, if you do download it and you go to the model library, you can type in Robby, and you'll get Robby the robot. And this is an evolutionary program, a program that demonstrates evolution, and it is based on biology. So it's based on each agent having a gene, if you will, and they two pairs will join together, mix genes, and have offspring. And that's basically how this system evolves. Now, the environment it lives in is extremely simple. Basically, it's a robot. It lives in a world of 10 by 10 squares, and it's got scattered with cans. So let me just quickly show you what it looks like. Here's the environment. So the robot starts in the bottom left corner, as you can see, and then those represent cans. These are all the cans it has to pick up. Now, if it bumps into a wall, it loses points. If it tries to pick up a can where there is no can, it loses points. It gains points every time it picks up a can. And so that's basically how the fitness is determined. It has 100 turns. So if I run through one of its strategies, so step through strategy, there we go. Oh, this one is not doing very well. It's trying to pick up a can. It just keeps trying to pick up a can. I didn't know what it was going to do. Let me see, 95, 96, 97. So there's none. Its final score is negative 99 because it kept trying to pick up a can where there was no can, and you lose a point every time it tries to do that. So this instructions on the right tells you what it's trying to do. And at the top, so pick up, move north. So it moved north once, and then it just kept trying to pick up a can. So it didn't do very well. But this is a randomly generated strategy, which of course didn't work at all. So the point is, each individual agent or robot, and there's 100 of them, what they do is they all try, I think 10 times on different environments. So if you view the environment again, you see the cans move around. So they keep trying in different environments 10 times, then they average the score, and then whichever one is best, it is able to reproduce, or is more likely able to reproduce, with another one, and they mix their strategies and then repeat, repeat, repeat. And that's basically how this thing evolves. And if you run it, this is what it looks like. Okay, this is Robby running. Now, this is the fitness level of the fittest agent in the system. And it's basically running around 10 points, which is, well, now it's going up. But 10 points is picking up one can, because you get 10 points when you pick up a can. This one here is an image of where all the agents are in relation to fitness and each other's strategy. The highest one is the fittest one, and then left to right, that shows you how similar the other agents are to the fittest agent. So top right is the fittest agent. Now this box here shows you the strategy of the best agent. I'm going to speed this up a bit. So here you can see it made a big jump, and now it's starting to climb upwards. And let's just fast forward it some more. And you can see it's more or less flat-lined. Well, it's gone up to about around 300. The interesting thing about evolution and the plateau it reaches, like a couple of things. Evolution does not always optimize the solution. It doesn't always find an optimal solution. That's not what evolution is about. Evolution is about finding a solution in an environment that is so difficult that it's almost impossible to come up with a solution in any other way. So the plateau is based on the way it made its solutions early on. So it builds a foundation. Now that foundation will give you a certain set of solutions, and that will determine how high you're able to go. And the only way that you can go higher once you hit your peak based on the solutions below is if you go back to basics and clear away everything and start again. So if I want this thing, for example, to go higher, the best way is to run this over and over and over and over again, and in one run it'll go quite high. It'll go over 400, for example. Okay, this is the best strategy. And if you recall last time I did it, it tried to pick up a can and then just stop there. So after evolution, this is how it's behaving now. And as you can see, it's much more sophisticated in its ability to move around and pick up cans. So now I've just shown you a accepted genetic algorithm. Now what I'm going to do is simplify it. make it much more circumstantial rather than computer controlled. So for instance, right now the computer is determining who's the fittest, then they're matching two fit parents in order to reproduce and create a new population, and then it kills off all the entire old population. So it's actually quite computationally intensive. What I'm going to do is change it so it's much more circumstantial. Instead of measuring fitness and looking for parents and so forth, we're going to scrap all that. We are going to change one thing, where the agents, instead of dying after every turn, they're going to live for 7 turns. Unless they're in the bottom 30%. If they're in the bottom 30%, they're going to get killed. So that's the only computation that's going on in this new one. The computer figures out who's the worst 30% after each turn, and they just kill them. And then random agents are chosen in order to create the new population. There's no measuring of fitness. Okay, so this is the modified genetic algorithm. So basically I call it the starvation version. And it runs slightly differently. As you see, it's a bit more spiky. And there's a few other detailed changes, which I'm not going to go into right now. But if anyone wants to know, I will tell you exactly what's going on. So just like the other one, we're going to move this forward a bit. This one's quite interesting because this one has a true plateau where it just goes completely flat, as I will show you right now. Now these plateaus are very typical of evolutionary systems. They'll do this and then suddenly go up, which I'm about to show you right now. Now this is another plateau, and it's going to go up a little bit shortly. Now as you can see, this has reached similar heights as the properly configured genetic algorithm. The difference here is I'm using starvation, or bankruptcy if you will, as the force that drives evolution. Note that using something like starvation or something like bankruptcy did not hinder the evolutionary system at all. This is crucially important to understand when I start showing you extremely simple evolutionary models that I'm going to introduce to you next week. Now you know a little bit about evolution, if you didn't already. And next week I'm going to show you the 2 simple conditions that I described at the beginning of the video and how they activate different aspects of society and the economy. Well, particularly the economy, and we're going to particularly be looking at price. Anyway, I hope you enjoyed that. I love evolution. I find it fascinating. And hopefully I'll see you next week.